Okay. Hello, everybody. Good morning, good afternoon, good evening, good night. Let's start our seminar for today. Today we have as our guest person Geordie Williamson from University of Sydney, Australia. He's well known, has many distinctions. He was invited speaker on International Congress of Mathematicians, on European Congress of Mathematicians, has premiers from American Mathematical Society, from European Mathematical Society, from Australian Mathematical Society. He is a fellow of Royal Society, of Australian Academy of Science, and has many other decorations. So we are happy to have him here. He will speak on spectra in representation theory. So please, Professor Williamson, you can start.
Okay, so thank you very, very much for the invitation. What I'm talking about today is very much a kind of research direction. I just want to explain in very broad terms what I think is something very interesting to pursue in the future. And then in the very end, I will explain some computations, which I did with Ben Elias, which suggests that something very interesting is going on. But at the moment, our computations are very limited and we have no conceptual understanding of what's happening. Okay, so just as a very broad introduction, I just want to remind you that in algebraic topology, historically, I guess the first thing that happened were Betti numbers, and then we discovered a rational cohomology, maybe integral cohomology, mod P cohomology. And of course, these are very interesting tools in answering basic questions in algebraic topology. And then very early on also, we learned about the homotopy groups. So there's quite a lot of noise in the background. I don't know where it's coming from. Anyway. And my understanding of a very rough I would say a potted history understanding of what happened is somehow there was this revolution in the end of the 1950s with the discovery of K-theory by, so the first proposal was made by Grassmannian, and then Atiyah and Batzebruch introduced topological K-theory. And then the idea of an extraordinary cohomology theory took off. And then over the next years, more and more extraordinary cohomology theories were discovered, and their relevance in algebraic topology is enormous. So something like K-theory. There's also things like elliptic cohomology, Morava K-theories. Etc. And my vague understanding of this is that somehow this is roughly in order of difficulty. So something like cohomology is rather easy to compute. K-theory is also rather easy to compute. And as you go into these cohomology theories, they become more difficult to compute, and they somehow give you better and better understanding of homotopy groups. Now, what's the situation in geometric representation theory? So basically we use cohomology a lot. Also mod P cohomology. We use kind of algebraic K-theory rather a lot. I mean K0. But also we have intersection cohomology. And roughly speaking, the point of this talk, which, as I said, is more of a kind of proposal of interesting future research, is to ask what's the kind of intersection theory here? What's intersection, what's intersection K-theory, for example? Yeah, so basically we want to put intersection into some questions in algebraic topology. And also we can ask, what about all of this stuff? Do the more exotic cohomology theories in algebraic topology play a role in geometric representation theory? And I should also say that basically in algebraic topology, if you're only interested in rational coefficients, we have a very good understanding of what happens. So this is the theory of rational homotopy theory, which is basically, my rough understanding is that it tells you that you don't need all of this business. So this business only comes into play when you're interested in torsion. So this should be particularly helpful for torsion questions. Which are these are the questions that I really care about. Okay, so that's a very rough introduction, and I should say that many people have asked about intersection K-theory in the past. Apparently, Drinfeld asked about this in the 80s. Merkovich definitely has asked about this rather a lot over the last kind of 30 years. So this is not at all a new idea. There's also a paper by Padurariu from last year called Intersection K-theory. So this is just one, one take on the possibilities of this subject, by no means exhaustive. So I just want to give a very kind of brief idea of where intersection cohomology comes from. Also, please don't hesitate to interrupt if there's a question. So where does intersection cohomology come from? So if we take X, and so this will almost always be a complex algebraic variety. We can consider the constant sheaf on X, and now its derived global sections constant sheaf is the cohomology of X. So there's some beautiful notes of Jacob Lurie on the internet called it's something like On Infinity Categories, where he explains that kind of in a first course we think about cohomology as being maps into our space, so singular chains or something like that, singular cochains. In the second course we learn about Eilenberg-MacLane spaces, and we learn that cohomology can also be thought of as maps out. But probably the best way of thinking about cohomology is it's something happening on X. Okay, and what happens on X is the constant sheaf in this particular case. But there's also a complex of sheaves ICX with Q coefficients. So this is the intersection cohomology complex. Whose global sections gives the intersection cohomology of X. Okay. So this intersection cohomology was first defined by Gretzky and McPherson via certain conditions on chains. So you have a stratification of X, and then you only allow chains which intersect the singularities of X in a not too deep way. So they restrict the possible interactions of chains with the singularities of X. And then, so they had a kind of more traditional take on this. And then Deligne apparently at a party at the IHES wrote down a definition of this complex for Macpherson on a napkin. And then apparently Macpherson very lovingly took this napkin back to the United States to study it for a year and understood what Deligne was saying. So you have this intersection cohomology complex. Now, there's a whole theory that provides this. So you say, you know, there's this abelian category of perverse sheaves, and these are the simple objects inside this abelian category. And they're given by some explicit recipe. But there's another different way of thinking about IC sheaves, which is by the decomposition theorem, which I want to state here. So I should say up here, it's possible to take, given any, so given any U inside X locally closed, and smooth, and given any L on U, we can associate IC U bar L, which is the intersection. One should think about it as being two. So in normal cohomology, you can take intersection. We can take cohomology with twisted coefficients, values in a local system, and this is the complex that produces intersection cohomology with values in a local system. Yeah. Now the decomposition theorem. So this is by Beilenson, Bernstein, Deligne, and Gabber, is the remarkable statement that for any proper map starting from a smooth variety, if we take the constant sheaf on X and push it forward along this map, then it breaks up as a direct sum of IC sheaves, of these intersection cohomology complexes. So this has many consequences, one of which is that the intersection cohomology of Y is the summand of the normal cohomology of any resolution. But it has a kind of more, like, another interesting consequence, which is basically that I could have discovered IC sheaves without knowing about perverse sheaves. And that's the basic idea that I want to, the basic proposal that I want to pursue in the next few slides. So this is meant to be a schematic of all algebraic varieties. Okay, so you know I can have and in this schematic I only consider smooth. So I only consider proper maps. So this is the category of algebraic varieties, but I only consider proper maps. And this is meant to be some kind of picture of the kind of proper maps that can exist. So I might have some covering. I'm only drawing curves, so I don't have very interesting maps, but here's a resolution. Here's some map collapsing further, etc. Okay, so I have this whole world. And now what the decomposition theorem tells me is that if I start with the constant sheaf on these smooth things and I'm allowed to push it forward, then I get far fewer sheaves than I would ordinarily expect. So roughly speaking, if I take the constant sheaf here and push it forward, it seems to know a lot about the fibers of the map, of fibers of this map. And so I would kind of naively expect to get the same, a kind of pretty faithful reproduction of all the sheaves that exist above my space in all the direct image sheaves that I get. But we get far fewer, which is kind of tied to the fact that maps between complex algebraic varieties are very constrained, often for somewhat mysterious reasons. So these are the points that I want to make. We get far fewer summands than we would a priori expect. We also could have discovered IC sheaves without perverse sheaves. So if we just lived in this world and taken this rule where we take constant sheaves on smooth things and are allowed to push forward, then we would have noticed that there's some special class of sheaves. And this should give us a route to understanding intersection K-theory, for example. So one definition, so what I want to explain in a second is it makes sense to take sheaves, for example, of KU modules, and that summands of these should be some analog of IC sheaves. So I realize this is a lot to digest and I'm being somewhat sketchy, but you know, if you feel that asking a question would help, please don't hesitate to do so. Okay, so roughly speaking, the parity sheaves theorem is just the statement that we get far fewer sheaves than we expect. So I just want to give a precise theorem. So this is by Jutel Meltner and myself from, I've got no idea, I'm guessing, but 2008 or something. So from some time ago. So suppose we stay in the world of, right? So basically what I want to say is that if we stay in a world like the one above, but we restrict the classes of varieties and maps that we can consider, then we get a similar statement to the decomposition theorem with mod p coefficients. So suppose we stay in the world of varieties with stratifications satisfying parity vanishing, i.e. H odd of the strata with whichever cohomology we're considering is 0, and all maps have and all fibers satisfy parity vanishing. Okay, so we live in this world up here, but we only consider stratifications of our spaces with such that the cohomology of the strata vanishes in odd degree and cohomology of the fiber vanishes in odd degree. Then the summands of direct image sheaves are classified by strata. So examples, this is a very restricted world, but examples of where this works are Schubert varieties. Plus Bott-Samuelson. Resolutions. Toric varieties. Nilpotent cones. Some quiver moduli. So I'm just saying that there's settings in geometric representation theory where this makes sense. So I would like to think about this. So one thing that I don't know that I think is very interesting is imagine that you just take all proper maps and mod p cohomology. So what summands do you get? And I kind of think of this as a meta theorem to guide us, saying that in certain situations we should just look for summands of direct image sheaves. So where are we going now? So now I want to explain that, I want to explain the world of spectra so this is something that's very new to me. So in some sense, I'm a beginner. It's very interesting, and I basically what I want to explain is how does this theory make sense to produce something like intersection K-theory or the parity sheaf and analog of K-theory. So these summands specified by strata. So these summands are called parity sheaves. So I want to give, so spectra are something like spaces, but they're not. I mean, they're not exactly spaces. And I want to give two motivations for why one would care about spectra. So this is a subject in homotopy theory. So the first basic point that I think is very interesting is that the statement that like homotopy theory, so that by this I mean the homotopy category of spaces, is almost triangulated. So it's almost a triangulated category. What do I mean by that? So if we consider the suspension of a space X, so this means we put our space and we cross it with an interval, and then we collapse the two endpoints. So this is like we kind of hang our space, we suspend our space between 2 points. Then, so maps between the suspensions of two spaces is an abelian group. And why is that? Here's the recipe for taking the sum of two maps. And if you want to, like a fun exercise, is what is minus f. Okay. So there's no way to add maps between homotopy classes and maps between two spaces, but homotopy maps between their suspensions we can add. So this is very analogous to the sum on homotopy groups. So that's the first reason that this looks almost triangulated. I mean, it's at least additive once we suspend. Another point is that we have distinguished triangles. So we almost have distinguished triangles. So if we take a map from X to Y, then there's the cone over that map. So here I take the cone over X, and then I glue the end of the cone. So I take the interval times X, collapse this endpoint, and then I glue this end to Y according to my map F. This is the cone. And now inside this, if we collapse Y, we get exactly the suspension back. And it's really a fun kind of topology exercise to see that this really does behave like a distinguished triangle. So for example, you know, one of the axioms is that turning a triangle is a triangle. And it's very fun to think about like why that's true here. Okay. But the problem is that this suspension functor is not invertible. So given a space X, it's not always possible to find a space Y such that X is the suspension of Y. And you can think about how you would go about formally inverting sigma, and this is what leads to spectra. So roughly speaking, I mean, this is actually not so rough. This is pretty, I mean, I think there's various senses in which this is exactly what the homotopy category of spectra is. So it spaces up to homotopy where we invert suspension. So so one of the ways to think about what happens here is that it's very interesting. It's very useful in algebraic topology to consider So stable homotopy classes of maps. So you consider classes of maps which survive after suspending some number of times. This is the category in which maps are stable classes of maps. So that's the first motivation for spectra. The second motivation for spectra is that so spectra are cohomology theories. So for any generalized cohomology theory, so for example, cohomology with values in an abelian group, or K-theory, or one of the others that I wrote down at the start, Brown representability tells me the remarkable fact that cohomology is always representable. So I can always find a space. So here's my fixed cohomology theory. So it has EI for I and Z. It has these functors. And no matter what my generalized cohomology theory is, its value on a space Y is always homotopy classes of maps to some representing space xk, which is defined up to homotopy. So this is Brown representability. So for example, normal cohomology is represented by Eilenberg-MacLane spaces. And now there's a very fun little thing to do, which is to ask yourself, what does the fact that this is a cohomology theory kind of mean for these representing spaces? I can't just chuck in any spaces, any sequence of spaces. And the answer is that we get a map from the suspension of xk to xk plus 1. And this is basically what a spectrum is. So we have a sequence of spaces together with a map from the suspension of xk to the next one. So yeah, so there's an adjunction which gives us a map back the other way, which probably makes more sense with this cohomology thing, but anyway, I won't. Okay, so some examples of spectra are the following. So the most basic example is the sphere spectrum, which has ith group, just the I sphere. If we take a space, we can consider a spectrum whose ith part is the ith suspension of X. So this gives us a functor from, so this gives us the functor from spaces, the spectra. If we apply this philosophy that kind of spectra are something like cohomology theories, that the thing that corresponds to cohomology with values in an abelian group is the Eilenberg-MacLane spectrum, which we denote HA, and its ith value is the ith Eilenberg-MacLane space. And so this H gives us a map from the passage to Eilenberg-MacLane space, gives us a map from rings or abelian groups. To spectra. And as an example of kind of a spectrum which is not of these easy forms, the K-theory spectrum, Ku, has, so it's a periodic spectrum, so it has the same, keeps having the same values in even and odd degrees. And these values are the classifying space of the infinite unitary group times Z, if I is even, and infinite unitary group is I is odd. And the kind of thing, the fact that this connects up to be a spectrum is related to what periodicity. So my understanding is that there's enormous kind of foundational issues in making the theory of spectra work. So basically, it's clear what the homotopy category should be, but not clear what it's a little bit like we have a derived category, but it's not clear what the category of chain complexes should be, roughly speaking. That's an analogy. But there's various ways around this. One of them that is nice for beginners like me is this thing called symmetric spectra. So there's basically a way to make spectra into a symmetric monoidal model category. And so you can talk about, for example, ring objects in spectra, or once you have a ring object, you can talk about a module object, etc. And I guess, why do we care about this? It provides one of the reasons is it provides a really remarkable place where kind of spaces and algebra can interact in non-trivial ways. So, yeah. So basically, given any, I'll delete this. So in some sense, this is just what I've only very recently learned, and it seems it's very fun to play with. Which is, so given any ring spectrum, so example would be e.g. HA for A a ring, or KU, or actually the sphere spectrum. We can consider modules over this ring spectrum, and this is what is known as a stable infinity category. Now, this is an analog of, if we take a ring, we can consider chain complexes of A modules. So one can think about this stable infinity category as something like chain complexes of A modules. And then taking its homotopy category, we get the derived category, and taking its homotopy category, we get we get a triangulated category, which is something like the derived category of A modules. And it makes sense to consider sheaves of A modules, and we have 6 functors. So I'm not sure if this is useful, but this is the way that I kind of think about this. So imagine that I want to explain to you what a sheaf is. I can say, sorry, not a sheaf. So imagine that I want to define the derived category of sheaves on X. So there's 2 approaches. The first one is to explain what the abelian category of sheaves is. Yes. And then I know that whenever I have an abelian category, I can take its derived category. And in some sense, this is the way that I think many of us think about the derived category of sheaves on a space. If I think about what is an object in the derived category, I think about it as being basically a collection of sheaves with differentials, and then I have to be a little bit careful because I'm in the derived category. So, but another way that I could have done this is explain, like, let's say we do sheaves of A modules. Explain what a complex of A modules is. And then, so view F inside here. as a gadget that sends U to, so some open set inside X, U to a complex of A modules. Okay. So this is the traditional route. This is a nice route because it basically, it kind of cuts out a step. But the difficulty here is that I need to formulate the sheaf axioms. So it's rather complicated to say what gluing means, because now there's a complex of A modules, and so here gluing is complicated but can be done. So if using the technology of infinity categories, it's possible to make sense of gluing. It's possible and even not difficult to make. Gluing is tricky. And the really nice thing about this is that it gives you access to a broader class of things that you would like to call sheaves on a space. Because whenever you understand what a complex of A modules is, you can understand what a sheaf of A modules is on a space. Okay. So a basic example to keep in mind is that if X is a space, we can consider, before we just took the constant sheaf with values in X and we got cohomology. Now it's possible to take a constant sheaf of KU modules and the global sections of this object, or more precisely its homotopy groups, give you the topological K-theory of X. And a very basic and important point is that very often interesting ring spectra have periodic module categories. So for example, in K-theory, and so we can't expect a T structure, and there's no notion of perverse sheaves. But the basic proposal is that with values in these, if we take sheaves of A modules for some interesting ring spectrum, there should be many settings in which the above kind of meta theorem holds. And so we should get objects on X whose global sections are something like intersection K-theory or intersection parity sheaves or something like this. And this proposal is very much motivated by work of Spencer Leslie and Gus Lonergan, who first kind of explained why it might be interesting to take sheaves of modules over spectra in the geometric Satake equivalence that I'll come to at the end of this talk. Okay. So I think now so that's the end of the general blah, blah, blah. And now in the final section, I just want to explain some computations which I think are interesting. So I want to briefly recall the geometric Satake equivalence, which is a really fundamental statement in geometric representation theory. So we start with the reductive group over the complex numbers. We can look at its dual group over the integers. So this is determined by some root datum, and we basically take the transpose, and we get by some Chevalier existence theorem, we get some dual group over the integers. So for example, if we just took GLN here, we just get GLN. But if you took something like symplectic groups here, you would get something like odd orthogonal groups here. And to this reductive group, we can associate its affine Grassmannian. So this is a really fundamental object. So you can think about it as in various different ways. So you don't need to know too much about it for this talk. If you don't already know, it's an infinite dimensional variety. So it's a direct limit of projective varieties under closed embeddings. So it's a little bit like P infinity or something like that. So P infinity, it can be thought of as the union of P1, P2, P3, P4, etc. Something like that. Here's an example for SL2. So this is a stratification. But notice that this looks a little bit like P infinity. So P infinity would also have C0, C1, C2, C3, C4. But the Grassmannian of SL2 is not P infinity, and the reason is that the way that these cells are glued together is rather complicated. And the geometric Tataki equivalence is the statement that if I take perverse sheaves on this infinite dimensional variety with convolution, then this gives me representations of the dual group. So the slogan is that the Langlands dual group may be recovered from the geometry of the affine Grassmannian, which is remarkable because when I explained how to construct this dual group, well, I appealed to an existence theorem. It's kind of weird. This operation we think of as absolutely central in mathematics, and yet the way to go from here to here is to say, well, you know, go and read Chevalier and convince yourself that this thing exists. Whereas here, we're actually giving a construction of the, whoops, my notation is not quite right. We're actually giving a construction of the dual group starting from our original group. So this works with coefficients in any field, or even basically any ring, in fact. Okay, so and now there's this very interesting proposal that was asked by Lurie, which is to describe this category, the category of, so I explained that given any ring spectrum, it makes sense to consider sheaves of modules over that ring spectrum. So the problem is to describe this category in terms of the dual group. And I don't know, I find this a really fascinating question because one of the ways to think about the sphere spectrum in homotopy theory is as being something like the integers, but much, much deeper than the integers. So in ring theory, the initial ring is the integers. In Spectra, the initial ring is the sphere spectrum. And so this is like, this should be some incredibly interesting thing that gives rise to a whole lot of different categories via kind of change of basis. Just as, so the Chevalier group scheme is a very basic and fundamental object over the integers, but this is saying that there's a kind of much deeper object somewhere that we don't understand at all. So this is kind of way beyond me in terms of trying to come to grips with it. But just as an experiment, we tried to put KU here to kind of get used to things and warm up a little bit. So one thing just that's important to remember is that in the Satake equivalence, so we haven't, this is an equivalence of abelian categories. It's equivalence of symmetric tensor categories. But it is not the case that this stays an equivalence when we pass to the natural ambient derived categories. So this sits inside sheaves on the affine Grassmannian, sits inside the derived category representations, and these are not equivalences. This is not equivalent. And so even with Q coefficients, if we're not allowed T structures, something more subtle is going to happen. So for example, here we would expect a functor from here to here without T structures, but we wouldn't expect it to be an equivalence on derived categories. So in this world of modules over ring spectra, you're basically not allowed to talk about abelian categories. So this is a famous result of Bezrok-Kamnikov and Finkelberg, which explains that what this full derived category of sheaves on the affine Grassmannian is in terms of the dual group. And it looks a bit like representations of the dual group, but it's a bit more subtle. And we expect something like that in general. Okay, so this is the expected, I called it expected theorem, which is, yeah, an expected theorem, but I think at this stage we have absolutely no idea how we would prove this. You know, maybe one should think about it as like a rough conjecture based on a few computations, which were nonetheless surprising. So we're trying to come to grips with what sheaves are on the affine Grassmannian, and we're taking KU modules. Now, one kind of basic point going on behind all this is that we know how to compute thanks to kind of Soergel bimodule technology. So we can take global sections, and what we get is R bimodules over the equivariant K-theory of a point. And so what we expect is that this global sections functor is a tensor functor, and it's an equivalence on homotopy groups. So given two objects inside here of a special form, I can compute their homs and x after applying this functor. And roughly speaking, what kind of really surprised us is if we put in KU, we get the quantum group. That's the basic point. But there's some subtleties here. So maybe I'll just go over the main points and then I'll finish, and if people have more precise questions, they can ask them. So the main points are, we have this monoidal category, we have a global sections functor. This is sitting inside some category of bimodules over a commutative ring. And now what we've checked is that there exists a functor from representations of the quantum group to this category. In the following cases, in the cases of A1, A2, and C2, B2. So we have this functor. And I should say that this is, it's really remarkable in the sense that we compute for a very, very long time, and then magically the relations of the quantum group kind of pop out. So what are the subtleties? The first is that we need to consider the affine Grassmannian for the twisted loop group. So this means that we need to, it's a basic issue that that Langland's duality doesn't commute with affinization. So the way that we see this is kind of amusing. So if you take the natural representation of SP4, the four-dimensional representation of SP4, for the quantum group, if we use the normal affine Grassmannian, we get a quantum dimension of 4, which is wrong. And what we want is 5 minus 1, which occurs when we put in this twist. Another very important point is that the Q in the quantum group here corresponds to the loop rotation C star. And I'll finish by discussing two other approaches. So it's, I don't know, this geometric hierarchy appears like a very central thing in my world. And so it's very natural to try to pursue a quantum geometric hierarchy. And Cautis-Kamnitzer have this beautiful work where they consider kind of algebraic K-theory of convolution spaces, and they prove a relationship with the quantum group, which is more precise than the one that I've just put up there for SLN. And roughly speaking, what Cautis-Kamnitzer are doing and what we're doing should be the same thing. There's a fair bit of unpacking to do, but I think that it's basically the same. And I think it's interesting that they didn't go beyond SLN, and the moment that we go beyond SLN, we see that we need this twist. And Gatesky-Lurie have this other approach using so we tick sheaves on the determinant line bundle. So this looks really different. So in their approach, Q corresponds to kind of monodromy, which is not loop rotation. So in the world of affine Lie algebras, their Q corresponds to C, and our Q corresponds to D. So the degree operator, which are fundamentally different. But there is some kind of causal duality that swaps these two. So one could hope for a relation one day, but I have no idea what that relation is. So thank you very much.
Okay. Thank you very much for your talk. Let us thank Professor Williamson. And now, any questions, comments, please?
I guess, hi, does this, would it make it possible to define versions of quantum groups associated to Morava K-theories? Maybe that's sort of relatively easy, but I don't know.
So is that Bert?
Yep, yep. Hi.
Oh, hi, Bert. Yeah, so roughly speaking, I really should have mentioned this very recent paper of Gufeng Zhao and Yaping Yang. So this is a totally separate thing, but they take Morava K-theories of Nakajima equivalence. And this looks like really beautiful work. And they explain, basically, so our motivation for this is that there's this philosophy that Lustig introduced and we've been pursuing of a kind of generations in modular representation theory. So that there's certain difficulties that are like related to P, and then there's difficulties related to P squared and things like that. And what we were trying to do in this project is understand that Morava K-theories provided these generational and basically it seems at this point, so from the limited amount that we've computed, that it kind of doesn't work. And so we're kind of stuck with K-theory, but in the other world of Nakajima equivalence, this work of Gufeng Zhao and Yaping Yang suggests that it really does work on the other side. So this might be one of these instances in representation theory where you work out something on, like there's this kind of dual world of geometric Satake and Nakajima equivalence, and sometimes things are much more transparent on one side, and it's very possible that we just chose the wrong side, and that Gufeng Zhao and that Yaping and Gufeng took the right side to understand this.
Okay. More questions, comments?
Georgie, can you comment a little bit about this last part about causal duality? So what kind of causal duality are you talking about at the end?
I mean, this I really don't understand particularly well, but one of the kind of really interesting things that happens, so I guess there's two comments to make here. The first is that that causal duality for affine in affine settings often swaps C and D. So this is, for example, in Resembling. And then the other really interesting thing is this recent work of Eberhardt, of Jens Eberhardt, which explains that kind of using KU modules gives ungraded causal duality. So in my world, for the last kind of 30 years or something, I don't know, in this Beilinson-Ginzburg-Zergel approach to causal duality, you always say, we have category A, category B. Category A and category B, their derived categories are not equivalent. However, when we realize that they both have these magical mixed structures, we upgrade and then they become derived equivalent, which is remarkable. But what Eberhard has seen is that if you put KU modules on the bottom, like you don't need to discover this magical grading, which is very exciting. So it's kind of, it seems to me that like the fact that we have this Bezel-Kamnikov-Yun swapping of C and D, and the fact that we have KU modules on our side and Gates-Greeley have basically constructible sheaves, you know, it suggests that this might be the relation.
I see. Okay.
Okay. More questions, comments, questions?
Hi, a question. So if you, I mean, it makes sense to take the Tate category of this Grassmannian with KU coefficients. And can you say maybe like, is there sort of Leslie Lonergan theory for that?
Yeah, so this is another motivation for why we were pursuing this. Yeah, so basically I hope, so yes, this is my hope, which is just extreme speculation at this point. But I would hope that we have some relation here, and that then there's a kind of Whittaker version of this theory, which then once you apply a kind of Tate type technology, gives you, for example, the linkage principle for quantum groups and character formulas and things like that, similar to what happens in the paper in my paper with Simon. But yeah, I haven't thought about like what happens on the affine Grassmannian, similar to Leslie Lonergan.
Thank you.
Okay. More questions? I cannot see. If there are no many questions, thank you very much, George. Let's thank our speaker. Very, very interesting. Thank you very much, really, George. Very, very nice, very interesting talk. And I want to make an announcement for the next Thursday. The next Thursday we will have talk by Vitaly Romankov from Sobolev Institute of Mathematics in Novosibirsk, but in fact he is working in the Omsk branch of this Sobolev Institute of Mathematics in Omsk University. Well, not university, in Omsk. The title to be announced. Well, that's all. Thank everybody, and if anybody, Geordie is here, still can continue with questions, not in less formal discussions maybe. Okay, you can continue. And that's all for, thanks everybody for participation. See you the next Thursday.